There are several different ways to analyze a blood gas, and for this week's lecture, we're going to focus on the traditional approach. There are only three components to worry about when we use the traditional approach. We need to know what is the pH of the blood, and how much carbon dioxide and bicarbonate is present in the sample. To get this information, we take a sample from the patient, a blood sample from the patient, and run it through a blood gas analyzer machine. The machine analyzes the sample and spits out the values for each of these components. In order to know how to interpret those results, first we have to talk about what is normal for our patients. The numbers shown here are the general rule of thumb for blood gas analysis in dogs and cats. The pH of the patient tells us how acidic or basic the patient's blood is. Normal pH for dogs and cats is about 7.4, give or take a little. A pH that is lower than normal is called an acidemia, and a pH that's higher than normal is called an alkalemia. The body really doesn't like to be outside of these ranges, and it's going to go to considerable lengths, including causing unhealthy problems in other body systems, to try and keep the pH of the blood normal. When the pH gets out of whack, the respiratory system and the kidneys are the two major systems that try to get things fixed. So we refer to these as the respiratory component and the metabolic component. Carbon dioxide from the respiratory system and bicarbonate from the metabolic system interact to try to keep the pH of the body as close to normal as possible. So, when the pH starts to get out of whack, we look at the respiratory component and the metabolic component to see what's happening. There should be a change in one of these systems to give us some clues about what's going on. We measure CO2 to tell us about the respiratory component of the buffer system. The normal range for CO2 in dogs and cats is about 40, plus or minus 4. If the CO2 is higher than normal, the patient has a respiratory acidosis. If the CO2 is lower than normal, then he has a respiratory alkalosis. We measure the bicarbonate to tell us about the metabolic component. When the bicarbonate is lower than normal, it's a metabolic acidosis. And when it's higher than normal, there's a metabolic alkalosis. So, the pH tells us about the acidity of the blood. It is called either an acidemia or an alkalemia. And then we look at what process is causing the change in the pH. These are the osis problems. You can have a respiratory acidosis, a metabolic acidosis, a respiratory alkalosis, or a metabolic alkalosis. So look carefully at these reference ranges. You might notice that when the pH goes down, this indicates an acid problem. So, helpfully, when the bicarbonate goes down, and the pH is also down, this is an acidifying process. But when you look at the respiratory component, the CO2 has to go up to cause an acidosis. So this confuses some people, but there is an easy way to remember. And that is, remember Rome. Rome stands for respiratory opposite and metabolic equal. This means that we're going to compare the CO2, is the CO2 moving up or down in comparison to the pH. So, look at the pH. When we talk about an acidic process, the pH is going down. So, in Rome, RO means respiratory opposite. So that means if the pH is going down and there's an acid and it's causing a respiratory problem is causing the acidosis, the CO2 has to go up. Respiratory opposite. And ME in Rome stands for metabolic equal. If the metabolic component is causing the problem and the pH is going down, then the bicarbonate has to go down when the pH goes down. The same is true when we talk about an alkalinizing or a basic process. When the pH is going up, meaning the patient is getting more basic, the bicarbonate will also go up if the bicarbonate is causing the problem. Metabolic equal. But if the respiratory side of things is causing the problem and the pH is going up, causing an alkalosis, then the CO2 has to get lower, respiratory opposite. One of the laws of physics is that for every action, there's an equal and opposite reaction. The body is kind of like that too. And so when we're talking about acid-base, that opposite reaction is called compensation. The body needs to have a normal pH to function well. This is why we measure the pH, so we can know if it's not normal and try to fix the problem. So when we talk about acid-base, the metabolic system is the opposite of the respiratory system, and acidosis is the opposite of alkalosis. So if a patient has a high pH because of a metabolic alkalosis, the compensatory response will be for the body to also get a respiratory acidosis, to try and cancel each other out and push the pH of the blood back to the normal range. I like to think about these as crisscrosses. The opposite of respiratory is metabolic, and the opposite of acidosis is an alkalosis. Alright, let's actually interpret some blood gases now. There are a lot of different techniques out there to use, so use what works for you. I'm going to show you two common techniques that I think are both pretty easy to use, Ultimately, though, if you find something that works better, I don't care how you do it as long as you're getting the right answers. Let's start with the stepwise approach. When you look at it in total, it can be a little bit daunting, so we're going to break it into easy to digest parts. Step 1 in the stepwise approach is to ask what is happening with the pH. There's only 3 possible answers. It can be low, it can be normal, or it can be high. So if the pH is low, we have an acidemia, and if it's high, we have an alkalemia. If it's normal, there's either no abnormality or there's a mixed acid-base disorder. We'll talk about mixed disorders in the next lecture. For now, just know that these are the 2 possibilities if the pH is normal. Next, we need to determine what the primary process is. So to do that, we're going to ask what's happening with the CO2 in the bicarbonate. And then follow the decision tree to decide if we have a respiratory acidosis, a metabolic acidosis, a respiratory alkalosis, or a metabolic alkalosis. This defines your primary problem. Don't overthink this. Just go with whatever you come up with right here as your primary problem. So then finally we get down to step 3 where we decide what sort of compensation is happening with our patient. There are expected compensations and those are listed here. But remember that the body doesn't always do what you expect it to do. So look for compensation and decide if it's present or not. Alright, so here's the full stepwise algorithm again. Now let's look at it with a real blood gas. So our patient has a pH of 7.19, a PCO2 of 22, and a bicarbonate of 14. If you look over here to the right, you'll see the normal values. So step 1 in the stepwise approach is to ask what is happening with the pH. There's only 3 possible answers, right? It can be low, high, or normal. The pH of our patient is 7.19, which you see is quite low. So our patient has an acidemia. We're going to go down the low pH acidemia path. Next, we need to determine what is the primary process. An acidemia can either be caused by a high CO2 or a low bicarbonate. So to determine the primary cause, we're going to ask what's happening with the CO2 and bicarbonate, or put another way, what parameter explains the change in the pH? Do we have a high CO2 or a low bicarbonate? Well, looking at our printout, we see that we have a low CO2, which does not match for the primary process, but we do have a low bicarbonate, which does match. So our patient has a metabolic acidosis. This is his primary problem. Again, don't overthink it. This is the primary problem. All right, our patient has a metabolic acidosis. Earlier, we said that the opposite of a metabolic acidosis is a respiratory alkalosis. We would expect our patient to have a low CO2, and he does. So he has a compensatory respiratory alkalosis. So our patient's acid-base diagnosis is a primary metabolic acidosis with compensatory respiratory alkalosis. All right, so stepwise algorithm. Very simple. You just follow the decision tree from top to bottom. Don't skip steps, and as long as you don't skip steps, you'll end up with the right answers. All right, now let's talk about the tic-tac-toe method. In the tic-tac-toe method, you're going to write the terms pH, CO2, and bicarbonate under the appropriate column in the tic-tac-toe grid. Then, you look at the component that lines up with the pH to determine the primary process. So, let's analyze a real blood gas. Our patient has a pH of 7.26, CO2 of 32, and a bicarbonate of 18. The reference values are all over here in the left corner if you need a reminder. So, a pH of 7.26 is quite low, so it goes in the acid column. The CO2 is low, and we remember from saying Rome that respiratory opposite, and that a low CO2 is basic, so CO2 goes in the basic column. When we see that the bicarbonate is low, and that means an acidic process, so the bicarb goes over here. Now, it's time to get a diagnosis. We look at what component lines up with the pH, in this case the bicarbonate, and we see that we're in the acid column, so the primary process is a metabolic acidosis. The CO2 is over here on the basic side, so there's respiratory compensation. So, the diagnosis is a metabolic acidosis with respiratory compensation. Let's do another one. We get our patient's blood gas printout and see this pH is high, so it goes over here in the basic column. CO2 is also moving in a basic direction, so it goes over here. And the bicarbonate, it's moving in an acidic direction, so it lands over in this column. Now, we're going to look at how things line up, and we see the pH and the CO2 are in the basic column together, so we have a respiratory alkalosis. The bicarbonate is moving in an acidic direction to compensate, so our diagnosis is a compensated respiratory alkalosis. All right, last one. We see the pH goes over here in the acid column. The CO2 is normal, so it goes in the middle column. And the bicarbonate is acid, so it goes over here on the left. The pH and the bicarbonate line up, so we have a metabolic acidosis. But look here, the CO2 is normal. The body isn't really compensating right now, so the diagnosis is a metabolic acidosis that is not compensated. All right, so those are the two different ways that I like to use to interpret a blood gas. You should have a few practice problems in your email that you can work through before next week to make sure that you understand. Please come find me or find a criticalist if you're having trouble with the practice problems, and we'll see you on Monday night.